right, so my talk is Are all BSDs created equally? A survey of BSD kernel vulnerabilities. So who am I? My name is Ilja van Sprundel. I work at IOActive. I'm the director of penetration testing. I do pen test, code review, and I break stuff for fun and profit, basically. And then it's somebody else's job to go and fix it. So my outline is sort of really easy. I have a one-slide introduction that sort of puts something out there, and then I tried to collect some data, which is essentially vulnerabilities over the years in BSD, or BSD kernels, and then sort of lacking more than what I want, I sort of do this sort of test by audit, and then basically I sort of run through some common attack surface and some issues I found, and then I sort of lay out some results and draw a couple of conclusions. So what's this talk about? Right, BSD kernel vulnerabilities, a comparison between different BSD flavors. The audience, I think, should be pretty self-explanatory, right? If you're a low-level security guy, or you're a Unix or BSD geek, or if you're a Linux guy, you might enjoy it too. Or people generally curious about, low-level OS internals. I think they might enjoy this. As far as knowledge goes, I do expect that you have some basic understanding of the BSD kernel. Doesn't have to be too deep, but just general concepts would be nice. Before I want to continue, this is not just, I didn't just create this out of thin air. There was work by others that I've sort of relied upon and sort of that came before me. And I'm sure I forgot some, because you always do. If you feel like you should be on the list and you're not, I'm the only guy at fault here. But all of these guys have basically had contributions at some level in sort of the offensive BSD kernel stuff. So this is my entire intro. It's basically a small rant by Theodorat from about 12 years ago, where he gave some Forbes magazine interview about the Linux guys and how they suck. And he follows up with some post online, and he goes, well, if the Linux people actually cared about code quality as we do, they wouldn't have had as many, local kernel holes in the last years. And he goes, how many has it been? Like 20 so far, right? That's the entire slide. And now that thing is 12 years old, but somehow that's been stuck in my head. I've never gotten it out. And I've been like, well, is that really true? Like, can you back that up? And so I went looking for some data. And sure enough, most of these things have CVs, and there's a website that collects them all. And you basically go there and say, please show me all Linux vulnerabilities, and it gives you this beautiful grid, and it says, these are all the bugs per year, types of bugs, all that type of stuff. And so if you look at this thing, you sort of see, from 99 till 2007, and this grid is actually slightly older. This is from about 3 weeks ago. The numbers for 2017 aren't quite right. It says 346 there, but it's really today, it's 353. That's the number of Linux kernel vulnerabilities this year, right? But if you start looking at sort of the top, 99 till about 2003, the numbers were pretty mild, right? It was like, 5 or anywhere between 5 and 20-ish, right? So that, and then sort of as of 2004, it kind of sort of, it gets sort of hockey stick that goes on, right? So the numbers basically get worse and worse and worse. More and more security vulnerabilities discovered and disclosed every year in Linux kernel, essentially, right? So now, what do those numbers look like for the BSDs? Well, I went to cvdetails.com and I said, OpenBSD kernel vulnerabilities, and zilch. It says NetBSD kernel vulnerabilities, nothing. FreeBSD kernel vulnerabilities, 0. Well, I know that's not true. I've had some reports on before. They should have at least shown up. But I do know they publish their own advisories. And I guess to get into OpenBSD, it's an errata. And it's essentially the same thing, except it's much shittier to get data out of. So I spent like an evening writing some a web crawler and some shitty pro code that parses HTML, and then fuck around in Excel to get the numbers lined up. But I did that, and so you sort of, build a similar-ish table, and you'll see that the numbers from 1999 till about 2003, more or less, are in the same ballpark as Linux. And then, Linux after 2003 kind of, goes like this. but then all the BSDs kind of sort of stay the same. I mean, they more or less line up, goes down a bit. It's usually anywhere between 0 and like 20 or something. And that hasn't changed. So if you look at numbers even for this year, they're more or less in line. So looking at these numbers, Theo was right. The Linux guys are doing a lot worse than the BSD guys, right? A very astute observation. And when he said 20 in 2005, that was, a very conservative view. If you look at the table here, it's 133, not 20. So, he was off, but his sort of the impression he wanted to give seems to sound right. But then I wonder, well, if we see this kind of hockey stick in the Linux numbers, why don't we see them in the BSD numbers, right? Is it really true? Is it code quality? Is that what it is? And so I want to sort of, in my presentation, I want to basically figure out, okay, are these numbers on equal footing? Are the Linux guys doing something different, or is everything else the same, and it's all about code quality? And so when I was thinking about this, I said, well, there's this many eyeballs thing, right? And I know, because it's many eyeballs thing is mostly like, this sort of, it's not really true. And of course, not all bugs are shallow. No matter how many people you have looking at code, some bugs are just ridiculously hard to find. But the general idea behind the many eyeballs thing I do like. And so I'm thinking, is there some truth to it? Because surely there are more eyes looking at the Linux kernel code than there are at OpenBSD, just by sheer number, right? And so I want to figure out if that has remotely anything to do with this. Okay, so first of all, I sort of looked around and sort of, has anybody else done this before, right? Because the way you would do this is you go and look for vulnerabilities in these things and see what the numbers are. And it turns out somebody did that 15 years ago. It's a very, very nice Australian guy named Silvio. And he did a Black Hat presentation about this. And I vaguely remember this, and I looked up the slides, and I'm like, oh, this is, you get nostalgia, you look at this again, and you're like, oh, these slides are so fucking awesome. And then you start looking at them, and then sort of get to the last 3 or 4 conclusion slides, and Silvio basically goes, well, there's really not that much of a quality difference between the BSDs and the Linux in terms of security. Now, that was over a decade ago, it was 15 years ago, so have things changed, right? His conclusions are 3 years before Theo's rant, so things may have changed in those 15 years, right? The time spent in the slides compared between BSD and Linux is like he spent like a week on all the BSDs combined and then like 3 months on Linux, right? So even like there, that's apples and oranges, right? And then the last one is sort of the Silvio basically put out this, okay, I'm going to go look for trivial integer overflows and some info leaks, and so that's kind of it, right? And so what I want to do is I was like, I don't want to limit myself to just those two. I want to be a little bit wider and see if I can find some other stuff as well and how easy those things are to find. So I sort of set out and said, okay, I'll go do the same thing Silvio did, just 15 years later. So I spend April, May, June, and a little bit of July auditing BSD source code. And when I set out to do this, I was like, okay, well, where do I think the bugs are? Where would they be, right? What's the interesting attack surface, right? And so you come up with this sort of short list of, where I think they are, right? Number one, I mean, it's stuff where a user can talk to it, essentially, right? So number one is system calls, right? Users are going to have to talk to kernel, and they're going to have to do it through system calls, right? Number two is obviously your TCP/IP stack, right? If you're network connected, someone's going to be sending you packets at some point, so that's attack surface. And so that's sort of the super common, that's the one that, my mom could come up with those. And then I sort of build lists that are like slightly less common to like, sort of rare-ish or exotic or something, right? And so at the top of the list is sort of the drivers and specifically, ioctls, because, most devices need someone to talk to it and configure it and get data out of it. And then sort of, I started thinking a bit more and I was like, oh, well, these BSDs, most of them, it comes with these compat layers. That's probably interesting to go and look for bugs. And then I was doing something else where I had this idea that I'll talk about in a second. And based upon that, I was like, oh, the trap handlers are probably interesting too. And this is where it gets sort of a little bit more and more esoteric. And then it's sort of okay, well, what about file systems? And it turns out there's some attack surfaces in file systems as well. And then I'm like, okay, well, there's also networking that isn't TCP/IP stack, like Wi-Fi. I mean, it kind of ties into it, but it's really, I mean, it's not. You open up TCP/IP to illustrate it. It doesn't talk about Wi-Fi frames, right? And then there's other things like Bluetooth and URDA, and I wanted to cover those too, but I ran out of time, so I'll just in that section only talk about the Wi-Fi stack. And then I was like, okay, let's just dive right in. And what I'm going to do is I'll sort of have a little slide that sort of introduces the thing, and then I'll show you a little bit of code of a bug, and I'll describe the bug. And for 4 or 5 of them, I'll basically run through a little bit of a demo. So let's start off with syscalls. Obvious attack surface, right? It is exactly how the user talks to the kernel. Without system calls, your OS would be essentially useless. Since the BSDs have evolved since the 70s, they no longer have 40 or 50 system calls. They number in the hundreds, and they do all sorts of funky stuff and performance improvements. And these, I mean, essentially these are things like open a file, read a file, create a network connection, read something from a network connection, close a file, send a message, get my UID. That's the kind of stuff it does, right? And so FreeBSD at the top of the list, they have like 550-ish. And then NetBSD is slightly below it with 480. And then at the bottom is like OpenBSD. They only have 330 system calls. And functionality-wise, you might say, okay, well, you want to have more rather than less because that have more functionality. And while that may be true, from a security perspective, the less system calls, the better, right? Because less system calls means less attack surface, means more security, right? So just looking at these numbers, you go like, oh, go OpenBSD, right? And then one of my assumptions is basically that, well, given that they're such obvious attack surface and they're so well tested and they're constantly used by apps, this is probably less likely to contain security bugs, right? And so let me show some code. So that's a system call. This one basically drops a syslog message, right? And it takes a buffer and it takes a length and it takes your buffer and your length and it passes on to this function called doSendSyslog. And doSendSyslog basically takes the length field and then basically puts it in an IO structure, and then from there it sort of takes out the length field again and then passes that along to the kernel malloc function. Now the kernel malloc function is sort of, historically in BSDs it was very special. The FreeBSD and NetBSD have sort of evolved away from that, but OpenBSD still has the original model where malloc basically goes and says, if your length is too big, you're doing something really horrible, and instead of just hanging your system, I'm going to crap out and basically panic. And then it looks like this. Your system is essentially dead after you do this. And so essentially this is it's an unbound malloc in OpenBSD that triggers a kernel panic. And it's easily triggerable through the SendSysLog system call. And let me see if I can, man, I really can't see that. Hold on. That's not it. What? One more? This guy? There you go, okay. So that's, I seriously, I can't see it because my screen is different than what's there. Anyway, so that should tell you the uname that it's NetBSD, OpenBSD, sorry, right? Yes, yes. And I precompiled the syslog binary, and I will be throwing the source code for that out after my talk. I just don't know where yet. But if you want to figure out where it is, shoot me an email and I'll tell you. So if we run this thing, boom, there you go. Right there, that's a kernel panic. The box is dead. Awesome, thank you. Okay, hold on. Yeah, looks about right. Okay, so that definitely triggers a kernel panic, right? Okay, let's look at a not system call because we don't just want to look at OpenBSD, right? So this is a system call called KLD stat, which is in FreeBSD, and basically you call a system call and you say, hey, give me a list of loaded drivers, or for that particular driver, tell me everything you know about it. And sort of this system call goes back and says, here's what I got. And the way that works is it calls this thing called copy in, which takes the data from the user, and then calls current KLD stat, and it basically collects a bunch of data and puts it in the structure called a stat structure. And I don't have the function for KLD stat in here because I didn't want to like pollute the slide. But essentially what this function does is it fills out two strings that can be about 1,000 bytes long, and it sort of copies a null terminated string into it, but then everything else after no byte is never initialized. So you basically end up with about a half a page worth of info leak stuff. It's just data that's on the stack, never initialized, right? This is in FreeBSD 11 is when I looked at it, went back and saw that this bug has been around for more or less about a decade. So let me see if I can demo that too. Okay, this works better. I think that one's right, yes. So this basically triggers the bug over and over and over, and what you're going to see is like a long stream of like random kernel bytes. Boom, there you go. All that stuff that's all, you're leaking and you're leaking and you're leaking. Yeah, there's some weird bug where sometimes it hangs, but it basically just keeps leaking and leaking and leaking and leaking. That's endless amounts of uninitialized kernel memory. I was thinking of doing a demo where I grabbed some stuff out of it, but I didn't, ran out of time. Oh, damn it. There we go, okay. So now I've seen two of these bugs, and I have several more syscall bugs. I didn't want to spend all my time just demoing those things. But essentially, the previous assumption where we go, oh, well, these things are well tested, they've been around forever, it's highly unlikely to have bugs. Well, that's not really true. Turns out bugs do occur in system calls with some regularity, and particularly newly added system calls, right? That do census selecting has only been around for one version. The KLD one happens to have been around for a decade. There's a bunch of others like I have a bunch of other like FreeBSD ones that show up. So the assumption isn't really true. Like if you just assume syscalls won't have bugs, well, it just isn't true. Okay, so let's move on to TCP/IP stack, right? Hopefully, presumably, everybody knows what that is and what that means. It handles networks. The low-level stuff, IPv4 and 6, UDP and TCP, and the sequence numbers, and IPsec, and how it all ties together, and then how you route it back and forth to userland app and those kind of things. This is obviously very well-known attack surface. It's been around forever. Again, the same assumption here is that this is very well-tested code. It's been around since the early 80s. Very unlikely to find security bugs in there. Right? So here's another piece of OpenBSD code. This basically takes PGP over Ethernet packets and sort of passes it on to this handler, and it sort of loops over the packet data, and it looks for a tag in a length. When it finds a tag in length, it goes into the switch, and the switch goes, oh, hey, this tag, this tag, this tag. In this particular case, there's an error, some error tag, in this case, I guess sname error, and it basically goes there and says, okay, let's set error message to this, and then set a flag which says error tag, and then end of the switch case, there's this code that kind of goes, oh, hey, if we got this particular error message, go in and go do this. And then they basically pull out the thing out of the packet. Before they can actually touch the bytes, and this is like a bizarre, they have these things called mbuffs, which are basically very specific buffer structures that are designed to hold network data, right? And there's all sorts of APIs around them to work with them, and so they're made in a way so you can chain them together so that if you want to like append or prepend or like switch stuff out as you're building a packet, that they work, right? And as part of that, before you ever touch any of these things, you're not guaranteed to have a continuous buffer, right? And so there's a function called pull down, and basically what pull down does is it says, okay, what I'm going to do is I'm going to look at all of these things chained together, and when I complete and it's successful, I'm going to hand you back, a buffer that is completely continuous, and you can start using that, right? And so it does that, and if that works, it goes on and does what it's supposed to do. Now, if that fails, it bails out, and it basically goes to this thing called done, and the done basically says, oh yeah, this is your original mbuff, let's go and free that thing, right? And so that code looks fine, except if you look at the man page for pull down, it says in the fine print, it goes, well, if pull down fails, it frees the mbuff, and then it tells you it failed. So what's happening here basically is if the pull down fails, the mbuff is freed, and then it goes and frees the mbuff again, right? So, a pretty trivial case of, double free. This isn't, I found in OpenBSD 6.1, it turns out it's been there for a decade and change. And then one of the things I did is I tried to cross-reference, because they do have a fair amount of shared code, so I tried to cross-reference, and I looked at the NetBSD code base, and I saw that in February of this year, they discovered this bug independently, and they fixed it. But there was never an announcement made. It was silently fixed. And so again, the previous assumption that this is well-tested code and it's highly unlikely there's a bug in there, well, that isn't really true. While this is well-tested code, it'll still have bugs. And the other thing I discovered is that, so these mbuffs are incredibly complicated, and it's very error-prone, right? To do it right and to never make a mistake, it's kind of hard. And one of the things is that a lot of APIs to sort of handle these things, it depends on their failure cases. So about half of them basically go and say, okay, if I fail, I don't free this buffer. And the other half go, if I fail, I'm going to go free these buffers, right? And so that creates this inconsistency where if you're a developer, right, and you assume the API frees on failure, and so you basically say, okay, I'm not going to free this thing because it frees on failure, but if the API really doesn't free on failure, then you leak memory. And then the opposite occurs too, right? Where if you go and say, okay, I'm pretty sure it's API on failure doesn't free, I'll go free it, you know, we just double free. So there's this sort of, inconsistency among API behavior combined with the complexity of the mbuff structure sort of creates this situation where it's pretty damn hard to get things right every time. Right. So let's move on to drivers, right? ioctls, everybody's favorite attack surface. Lots and lots of drivers are out there. BSDs are no different. They have piles and piles of drivers for all sorts of stuff. Obviously BSD is a Unix, and in Unix, everything is a file. So the way you expose a device to userland is you put it in /dev, right? And you give it some name. And obviously these things basically expose file operations to userland, right? Like file and open and read and write and ioctl and things like that. And I guess you can mmap some of them too, things like that. So, ioctl obviously is where you have attack surface. Okay. So let's take a look at an ioctl, right? So NetBSD has this device called crypto. And basically what crypto does is it takes an ioctl input and actually, it takes an ioctl input and it basically goes and says, okay, well, here's some structure that comes from userland, and it contains this count field. And what we're going to do is we're going to create an array of number of count fields, and then we're going to start running data into it, right? And then we're going to start using it, and we're going to start manipulating stuff. And as you can see, there's a count times size of the structure. And anybody who knows anything about writing code and security knows that that is a very classic integer overflow. Right, that's an integer overflow right there. And that's your memory corruption bug right there. I didn't want to put more code on the slide because it would just pollute things, but that crypto dev mkey stuff is basically, starts writing stuff to that buffer that was previously allocated. So yeah, that's classic integer overflow leads to memory corruption. It's in NetBSD. It has been there about 9-ish years. And then, hold on, let me see. Okay. Yeah, let's yeah. So this is basically, hopefully, fingers crossed, going to trigger the integer overflow and then cause memory corruption, and it'll basically trap into the debugger. There you go. Boom. It's done. It's gone. Memory corrupted, rebooted. So here's another one. This is a device on FreeBSD called KSIMs, which basically gives you the ability to expose kernel symbols to userland, right? And it basically, as I mentioned earlier, most of these drivers have an open callback, and this one's no different. And when you call the open system call, it goes to this callback, and the callback basically sets up a few things so you can later do operations on it, and then it returns successfully. One of the things it does in this case is basically so it creates a file descriptor storage specific private data, which means there is kernel private data associated with the file descriptor you're going to use in userland. In this particular case, what they do is they look at the pointer to your that basically contains all the data needed to describe your virtual address space for your process, and stores it in that pointer, or inside that driver specific storage. And then basically return successfully. And then later on, there's another system call that basically gets called if you do an mmap in that particular file descriptor. And as you can see, it references that particular pointer that was previously saved, right? That SCP map is saved here and it's referenced here, right? Okay. So the bug here is that the pointer used in mmap doesn't necessarily still have to be valid than the one used in open. Right, and so the way that works is, because usually you say, okay, well, the file descriptor is associated with the process, and so as long as the process is around, the file descriptor will be around, and so that virtual address space map will still be around. Except, OpenBSDs, or at least the BSDs and Unix in general, is smarter than that, and it gives you the option to basically not just hold on to a file descriptor, but instead go to a different process and say, hey, you can now have this file descriptor too, and then once that guy has the file descriptor, you can say to the original process, okay, well, you go and die. So the original process is gone, and so all data associated with it is entirely gone and expired. And now you have that second process, and that second process is still holding on to the file descriptor, and all of a sudden it says, oh, well, now sounds like a good time to call mmap on this thing. And mmap goes around and says, oh, look, I have all these pointers to this particular process, this virtual memory space, and it goes and references that. So there's all sorts of things with that. Except the original process is gone, it's dead, it's entirely expired, and so this guy ends up, if you do that, it ends up doing really, really horrible things. And I would love to demo this, but well, I have a POC, because it's a shitty race to hit. This one took me a couple of days to hit. I don't have that long to show you. I will be releasing code, so if you want to play around with this, you can. For now, you'll have to do with a screenshot of a kernel panic. Okay, so that's it for the sort of super common attack surface. So the compat code is another one where it's like, okay, this is interesting attack surface. And so the one there is basically, so most BSDs have this thing where they offer additional binary support. So for example, FreeBSD, NetBSD, and up until a couple of years ago, OpenBSD had support for Linux. What that means is you could have a Linux compiled binary, you would run it on FreeBSD, and it would just run. Not just, because you have to set up like an environment, but by and large, the binary would work. And it could do other things like, emulate a 32-bit environment of the 64-bit version of that BSD you have, and it could do like older versions of DOS, things like that. And the way that works is basically what they do is they emulate a whole bunch of system calls. They fake as the system call that you expect it to be, and then they sort of funnel it to the real system call, and then sort of parse the stuff back and forth. Now, compat layers are a great idea from a user functionality perspective. They are an absolutely terrible idea from a security perspective. And Theodorat, who's the leader of OpenBSD and a pretty damn good developer, had some really interesting insight about compat layers. And if anybody would know, it would be him. He goes, well, people who rely on this stuff don't care enough to maintain it, and the people who work on the actual kernel don't give a damn about the compat layers because they don't use them. He says cultures are underlined in the same direction, and then he says compat layers rot very quickly, which means you write one today and tomorrow it's going to be just useless and just have nothing but security bugs in it. So here's the NetBSD. It's this like SVR4, which is like fairly ancient Unixy thing, and they basically emulate that on NetBSD. So if you have an original binary compiled for that and you move to binary NetBSD, it'll still work. And it has this thing called streams, which is sort of a predecessor to sockets-ish. And so what they do is, NetBSD doesn't support streams, so what they do is they fake it and they sort of put a socket underneath. And so the original SVR binaries will then think they have a stream even though it's a socket. And so this thing basically, it's essentially an octal that's supposed to do a socket operation. And they copy in some data structure and they put in this BND structure and they pass it on to this net adder to sock adder in. And net adder to sock adder in basically looks at this structure and it says, oh, this thing contains a 32-bit offset inside the structure. I'm going to use this offset and I'm going to add it to my pointer and I'm going to give you back a pointer to where you can start reading from. Problem there being is there's absolutely no validation being performed. And so basically you can end up with a wild pointer that points anywhere, which you can either use to trigger kernel panic, your box goes down, or you can, if you know what you're doing, very selectively pick pieces of memory and start leaking, very select pieces of kernel memory. And then what's really beautiful is at the top of this file, someone said, well, we're going to pretend we have streams. We don't really. Oh, yeah, and by the way, this code's really gross. So yeah, this was found in NetBSD 7.1, but this thing's been around for 21 years. It's been there since NetBSD 1.2. It's been around for a very, very long time. And it gives you the ability to read arbitrary-ish kernel memory or cause kernel panic. And so I submitted this bug to the NetBSD guys, and they go, oh shit, yeah, this thing is a total piece of shit. And they go, we fixed a gazillion bugs in this SVR4 thing. We should have never enabled this by default. It is an absolute minefield. And so when I submitted the bugs and they fixed them, they also changed their OS config file and be like, and basically turn off SVR4 support. If you want it now, you're going to have to recompile your kernel. Okay, so another thing I was thinking, I was like, okay, we have these things called trap handlers, and this is where things get a little bit exotic. So trap handlers are these sort of callbacks that that like very low level OS code registers sort of when it boots up, and it goes to the OS, or the OS basically sets things up, and so when some kind of a hardware thing happens, these things get called, right? Some kind of an exceptional fault happens, and these are things like division by zero, a system call, a breakpoint, invalid memory access. When the hardware sees any of these things, it sort of goes, oh, I don't know what this is, but I'm going to call this function pointer, and we'll have that deal with it, right? Some of them can be triggered by userland, some of them can be triggered by kernel, and the kernel has to trigger them correctly. The thing with trap handlers is that they are unbelievably nasty pieces of code, and exceptionally architecture specific. Every architecture and like every little minuscule like little diff will have, between architectures things are very different, and then every little diff within architecture might still have like tiny little changes between them. It's an absolute pain to try and understand these things, and it's ridiculously painful to look at this code. So I didn't look at it. So I said, okay, but I'd still like to play with this a little bit. Where do I go from here? And I was like, okay, well, what can I do to trigger exceptions and faults? Well, what if I just start executing random instructions? What happens? Surely that'll trigger a bunch of exceptions and traps, and then the OS has to handle it. And then I have a slightly more bigger fuzzer. This is essentially it. This is a sort of a one-slide trap handler fuzzer, where essentially what you do is you map a piece of code, read, write, or executable. You sort of start a loop, and every time you get in the loop, you basically, read out of def random, a page of random garbage. You fork off a process, you hand that page to the process, and the process basically goes function pointer call, and then surely it crashes, and it does this over and over and over and over and over again. And essentially, I did this on FreeBSD, and there's a accent trap that kind of blows up my face, and then and there's some other signal stuff that sort of blows up. And I have a demo of this. I'm not sure if it's going to work because this thing sometimes blows up fast, and sometimes it takes a while. But I can at least try and show this thing. Hold on. Oh man, this is so horrible. God damn it. I got him. Okay, there we go. Awesome. Wow, look at that. This is a horrible setup I got here. Plus my eyesight sucks. So this basically forms off browser processes. I don't know if it'll I may have to come back to it later because give it a few minutes, it might die.
So these are all crashes of that second thread, but without anything.
Yeah, this doesn't crash the kernel yet, but eventually it'll crash the kernel. If we're lucky, fingers crossed. I got it to hit earlier this morning, and usually it only takes a couple of minutes, but it's like random garbage, so it's like.
How are you recording which values cause crashes?
So not in this version, but I have a version that basically has a UDP socket and sends it to a server. And so the server basically goes and says, okay, this is the garbage you generate, this is garbage you generated. And so when it crashes, I look at the last packet and I go like, okay, let's decode what this set of bytes are. Like you can feed it to like IDA or something, and it'll tell you this is what it means. Anyway, I'll get back to this later. I hope it dies. But essentially, so yeah, there's a send trap I hit, and then there was another send signal trap I hit, which is this one. And so hopefully I can show this in a little while. So let's move on to file systems. So obviously when you think file systems, you say, okay, well, you have a file system image and you can mount it, and obviously if you, or have a USB stick and plug it in and have that mounted, and if somebody doesn't parse the file system correctly, then, bugs show up, right? That is number one. That is an easy attack surface. There's another one that I was playing with, and I was like, okay, that could be interesting. So in the last couple of years, all three of the BSDs have built-in support for Fuse. And I don't know if you guys know what Fuse is, but Fuse is essentially a mechanism that allows you to have userland file systems. And the idea being there is that, writing file systems in kernel is really, really hard. And so if we move to userland, it's okay if your file system does something bad or crashes. The OS won't go down. And so what that requires is your normal BSD VFS layer now has to support a file system that's in user as opposed to one in kernel. If kernel to kernel is talking, everyone's trusted. If kernel to user is talking, they're not trusted. So you're now taking this layer that is always talking to someone that it's trusted, and you're basically now feeding it a bunch of data from userland that's no longer trusted. So the VFS layers in theory should have been hardened for Fuse. So I looked at Fuse for all three BSDs, and basically sort of my impression was that NetBSD, Fuse, this is funny, right? So they're family, right? They all fork from each other, except when Fuse came around, they all said, no, we're all going to sort of make our own little thing. And so you have three distinct Fuse implementations for the three different BSDs. And so NetBSD sort of, in my view, made the most complete implementation, which allows sort of for the most options and flexibility. FreeBSD, I think, has the most controlled one in terms of the amount of stuff they'll take from userland in terms of a file system is highly controlled. And so what that means is there's relatively little opportunity for consumers to make mistakes, but there's more opportunity for the parsing inside the fuse code itself to make mistakes. And then OpenBSD sort of has sort of this minimal implementation. And then they all, none of them implement directly, but they implement all of the other file operations. Damn, I'm going to have to skip through this because I've got only a few more minutes left, I think, and there's conclusions I want to get to. But anyway, this is the get CW system call for the BSDs, for OpenBSD, and that you can hit that from Fuse. Anyway, let's skip over to file some stuff. Yeah, the network is interesting. You know, there's some bugs in the network stack where if you send a packet, the box goes down. Blah blah. Oh, and this is one of these things where there's all these wireless drivers that have like these straight up heap smashes where they're not expecting a malicious radio, even though they're taking data over USB. And so if you have a malicious radio, all of a sudden the OS has all sorts of heap overflows. But let's skip through that. Right, there's some miscellaneous stuff I want to talk about, but I don't have time. What? Oh yeah. So yeah, results. I looked at this stuff for about 3 months. I found about 30 or so bugs in FreeBSD, 25 or so in OpenBSD, 60-ish in NetBSD. And the thing is, it's hard to, because I give approximate numbers because some of these things are like, it's a single function and it contains 5 buffer overflows. Okay, is that 1 bug or 5, right? So I try to sort of be like, it's this many. Depends how you sort of look at these things, but I think these numbers more or less make sense. In terms of bugs I've seen, it's like a very long list of, I mean, there's the straight heap and stack smash like in those wireless drivers. A couple of race conditions, expired pointers, double freeze, recursion bugs, integer issues, very, very interesting ref count issues. Obviously overflows, but also there was one NetBSD bug where they're like, okay, we'll take a ref count on this V node, and then, okay, we're going to take the mount point out, and then we're going to drop the ref count, and now we're going to play with the mount point. Well, there's nothing tying them together, so if the mount point goes away, you're hitting wild pointers. Anyway, other things that I found were info leaks, out of bound leaks, null refs, logic bugs, a typo where they literally called the wrong destructor. It was something TX, and they call it something RX. Division by zero bugs, kernel panics, and memory leaks. So, found bugs in all 3, and basically, you know, in the attack surface I discovered, I mentioned earlier, and sort of among the range of the bugs that I just listed. Winner loser is, in my impression, fairly easy. When I started looking at this stuff, OpenBSD came out as a clear winner for a number of reasons. They have massively reduced their attack surface. They got rid of low-level module support. They have relatively few devices. Got rid of all of their compat code, including Linux. They deleted their Bluetooth stack because it sucked. They have more than 200 less system calls than FreeBSD, and they cut support for a bunch of really shitty architectures. On top of that, when Tio said they care about code quality, they do. They have virtually no integer overflows or sinus bugs. They're as good as gone in most places, except the ones where they didn't know about the attack surface, like the wireless drivers. And then also very few info leaks. So the bugs they know about and the patterns that they know, they look for them, you know, like a madman, and they eradicate them. NetBSD is one of these where it's like, okay, comparatively, they're the clear loser. Tons of legacy code and compat code, so that's, you got attack surface right there. They seem to be less consistent when it comes to code quality, and too many sinus bugs. And I know how this sounds, but, and I'm not trying to diss them because I know it's incredibly hard to write an OS, right? If you think it's easy to build, maintain, improve an operating system, you should try it. It's really hard, like you will cry yourself to sleep. And then somewhere in the middle is FreeBSD. Now, when I start reporting these bugs, sort of here's the response I got, right? When I emailed the OpenBSD guys, it took about a week or so to get a mail back from Tio. And first, he's like, oh, you know, I'm so sorry it took a week. I was out on vacation. And then within, after that week, like bug fixes started rolling out, the next couple of days. Everything got fixed within the 2-week period. FreeBSD guys responded as well in about a week or so, and then found total bugs. I don't know the exact status of the bugs. NetBSD, and this is where they really shine though. So I was kind of a lazy bastard, and I was sort of procrastinating, and I was like, I don't want to write up all these 60 bugs. So I only got them written up right before I got to Vegas. And so I sent him these bugs a couple of days ago, which is really unfair of me. And I was thinking like, how am I going to deal with this? I don't want to make him look bad. And then something happened that was ridiculous. They fixed all 60 bugs overnight. Which is unbelievably impressive. And I told him that. And I told him, if you want to call me out on being an asshole, you can. But I am in awe of you guys, because that is insane. Additionally, they also turned off SVR4, which I think is a great deal. And when they emailed me back, they said, we've disabled this thing, something we should have done a very, very long time ago. So yeah, pretty much, and my slides more conclusions. Bugs are still easy to find. Various levels of quality. Most consistent was OpenBSD. One more point I want to make is maintainers of BSDs should talk to each other, because I had several bugs where one guy had the bug and then the other guy fixed it 6 months ago, right? And it goes both ways, right? It's OpenBSD and NetBSD and FreeBSD. I got another funny story about that, about a guy I met at a bar yesterday who was a former OpenBSD developer, but I don't have the time to get into it. Code bases is OpenBSD is the smallest, FreeBSD is the biggest, and so it's interesting to look at these things. It's clear OpenBSD has the least amount of attack surfaces. FreeBSD likely has the biggest one. This obviously plays a part. If you don't have code for something, then you can't have bugs in it, right? And there's a thing between accidental versus planned, right? Some things didn't get implemented, just you didn't get to it, and other things you made a conscious choice to sort of get rid of it. The many eyeballs thing, I think it's a factor. Based on my results, I think it matters. I think code quality alone doesn't account for a discrepancy. I think code quality has something to do, I think the many eyeballs thing has something to do with it. My view is that, say what you will about the guys looking at the Linux kernel, and you can say a lot about them, there are just simply so many more of them, and it shows in the numbers. And then this thing sort of the presentation got out before I did this thing, and so the internet saw this, and they, had some questions, and I pretty much out of time, but I want to, because somebody asked about Dragonfly BSD, and I did not look at Dragonfly BSD. I considered it. Maybe I should have. I just didn't. I ran out of time. And then some links, and then that's pretty much it. I think I'm out of time, right? Awesome.